Hi, everyone. Just addressing your feedback from today. Is the rate for all reactants and products the same, or does it depend on the mole ratio? Yeah, short answer is it depends on the mole ratio. So let me give you a quick example or a simple example. 2A plus B going to 3C's. So we'll frequently end up using like these example type formulas because we'll at some point we won't care the identity of the chemical reactants. We just care about their stoichiometry, how many of them are produced for a certain amount of another reactant. So we just want to look at their relative ratios. And yeah, we will, when we're talking about the rate of a reaction, generally speaking, the rate of reaction, how quickly does that reaction occur? We will frequently describe the reaction as not being dependent on a single, not from the perspective of a single chemical species in that reaction. It could be, we can look at it from the perspective of A, we can look at it from the perspective of B or C, so we can ascribe or we can create some general, like just, I'll put it in quotes, general reaction rate, something that is just characteristic of the reaction as a whole. And that chemical reaction, we will frequently want to quantify it by looking at the rate of change of one of the chemical species. So I might want to say, okay, it should be related to a change in the concentration of A over time. But one of these reactions, one mole of this reaction requires 2A molecules. So I end up dividing out by its molar coefficient. And you'll end up doing that for all of these. You'll say the rate should be actually 1 over the molar coefficient. Also, because A is a reactant, I expect its concentration to decrease with time. And since we will frequently want to describe the reaction as some positive value, if the reaction rate is a change of, if A is decreasing over time, that's negative, so I will enforce a negative for that particular expression just to make sure my reaction rate has a positive value. But short answer, to recap your question, does it depend on the mole ratio? Yes, it absolutely depends upon the mole ratio. Now, the rates of change of each of them relative to each other, those also depend on their mole ratios, and I'll discuss that in just a second here because I had another question about, can you go through that derivation of where the 1/2 comes from? Could you further explain why the rate was minus 0.2 molar per second? So I'll explain that by looking at this particular sample expression. So when I have the 3 here in front of the carbon, it's not a carbon, it should just be C, and B is just B, but I'm sorry, I'm going to call them carbon and boron just because it's easier. It's actually easier for me to say that. I get 3 carbons for every boron that I lose or react. So the amount, so I'm going to write that as a sentence and show you how you can transcribe it into an equation. I would say amount of C is 3 times more than B. So frequently a handy trick when you're trying to transcribe or translate a mathematical sentence like this into an equation is that the is becomes your equal sign. So I would say moles of C is actually 3 times as large as the moles of B. And yeah, that's where the 3 comes from. I get 3 times 3 carbons for every mole of B. If I start with 1 mole of B, I end up with 9 moles. Sorry, 1 mole of, sorry, if I start with 3 moles of B, I end up with 9 moles of C. So C is 3 times larger than B. So if I translate the moles here into molarity and I relate them to rates, I can then say that the rate of change of C is 3 times larger than the rate of change of B. And if I want to, again, try to equate these or make some general expression here, oh, I should also have a negative sign here because I'm producing C, but I'm losing B. Then the negative of that sign there takes that into account. If I want to try to make some general statement, I would frequently move at 3 over here. So I'll say rate of B is equal to 1 over 3 rate of C. And so, point being that in general, that's why it ends up being shifted back over. You end up with 1 over the molar coefficient. So it is seeming, I admit it's a little counterintuitive. It looks like you multiply by the 3, but if you're looking at the relative ratios, you recognize C is actually 3 times larger than B. So this is not an equation, it's a recipe. It shows you how it changes. The equation ends up being a little bit more finicky than that. When do reverse reactions occur? That's a great and insightful question. Generally, so I'll answer it first for you. Reverse reactions can, in theory, happen all the time. So in the reaction that we did today, as soon as I mix them, the forward reaction starts happening. And the reverse reaction started happening. The sulfur actually starts starts converting back into the thiosulfate ion. But that reverse reaction might be very, very slow. Why might it be slow, especially at first, is because there wasn't much sulfur to begin with. And the rate of the reverse reaction is dependent upon the concentration of sulfur as a reactant. And if the concentration is low, then that reverse reaction is going to be slow. So generally speaking, when we talk about rates in the chapter on kinetics, when we start talking about kinetics, we are basically going to assume we're going to kind of ignore reverse reactions for a while. We think about them happening independently. They're not independent, obviously, and they're happening in the same system, and they are coupled together. But we will think about them at first as though, okay, we'll look at just the reaction in this direction. We'll only talk about the rate of reaction in this reaction. Later on, we'll come back and say, okay, technically the reverse reaction is also occurring, and we can look at that rate separately. So this reaction rate here, the rate of reaction that we've been talking about, has implicitly been the forward rate of reaction. But when do reverse reactions occur? They technically can occur at any time and do occur at any time. Yeah. Does a positive rate and a negative rate that equal each other mean the reaction is at equilibrium? So here's again when we need to sort of be careful. We usually think of the reaction rate as being positive. So the forward reaction has a certain rate, and the reverse reaction has a certain rate. So your question was, does that mean when they're equal and opposite, does that mean the reaction is at equilibrium? The reaction is at equilibrium when the forward reaction rate is equal to the backwards reaction rate. If they're equal to each other, then they should have the same value and they should have the same sign. So they should both be positive. When positive and negative rates come into play is when you're looking at the actual rate of change of individual chemical species in the reaction. So they are frequently lumped together. They are frequently treated as though they're the same thing. They are technically not the same thing, and it's a slight mathematical distinction between rate of reaction and rate of change of reactant concentration. One is directly related to the other, but they are separate entities, conceptually speaking. We will frequently try to equate them, but then we just have to make some distinction. Okay, reactant rates, they are implicitly they are negative. The reaction rate is reactant change rates are frequently negative. Reaction rates is just like a conceptual concept, a conceptual construct, are explicitly positive. So So yeah, there's that. So point being that equilibrium occurs when forward reaction rate is equal to backwards reaction rate. Those should both be equal and have the same sign. Rates of change, if you're, well, here's a great way. Here's why I'll say how you can recognize that they are distinct entities. If you're at equilibrium, if you are at equilibrium, then the system, at least to our conception of it, is no longer changing. So if it is at equilibrium, then the rate of change of a... Pause this video for just 1 second and see if you can get what this should be equal to. Okay. If you're at equilibrium, the rate of change of the reaction should actually be, the rate of change of one of the reactants should be 0. The reaction has quote unquote stopped, or at least it appears as though it's stopped. You're not producing more A and you're not producing more C, which means that their concentrations shouldn't be changing. When we first start talking about reaction rates, we are assuming the system has not yet reached equilibrium. And so it makes sense to say, okay, the reaction rate is related to the change of the concentration. So again, that kind of gets back into what I was saying, that at first we're not going to really consider reverse reactions. We're going to just talk about just the forward reaction, in which case it doesn't make sense to talk about equilibrium just yet. Okay, can colloidal suspensions always be observed visually? Yes, generally so. A key characteristic of colloidal suspensions is that the vast majority of them do scatter light. So they will either be opaque, meaning they just completely block light, or they'll be translucent, meaning that they let some light through, but you can't see distinct shapes. They're not transparent, they're translucent. Solutions are inevitably transparent. So either like a pane of glass or a window of glass or like a color or a stained glass window. Those are all transparent. Translucent would be like if you had an etched glass would be translucent. Colloidal suspensions are frequently translucent, often opaque, and almost never transparent. So you can observe them visually in that sense. I don't understand where rate constants come into play with the rate law. So let me just talk about the rate law here. So I'll give you an example of a rate law. This is not the only example of a rate law, but I'll just say this. So rate law, rate should be equal to a rate, sorry, the rate of reaction should be dependent on the concentration of one of the reactants. So I'll say B, and I'll say that it happens to be second order. It goes as the square of the concentration of B. So where does the rate constant come into play? Well, it kind of needs to be there for the equation to make any sense at all. What do I mean by that? Well, check the units. The units for rate should be molarity per second, how the molarity changes as a function of time. Get a better marker here. The concentration of B here, it's going as the square of B. So it goes as molality squared. So in order to just, if for no other reason than units alone, there needs to be something else here, some other mathematical object to get me from units of molar squared to molar per second. So there needs to be something here that has units of 1 over molar second. So when I multiply these two guys together, I get something that has molar per second. So that thing is the rate constant. We said rate depends on concentration. Concentration has units of molarity. Rate has units of molarity per second. So there has to be something else there to actually convert just concentration meaningfully into a rate if I want to try and look at a mathematical relationship between the two of them. That object is the rate constant. So that's what that's maybe not the most intuitive explanation of what the rate constant is, but that's how it factors in. That's why it comes into play in the rate law. Now, what the rate constant means is a fundamental measure of how fast a reaction tends to occur. So we discussed how, okay, the reaction does depend upon concentration, but there has to be something else to convert it, again, from just concentration into something that depends on time. And that other thing is the rate constant. The rate constant represents just generally how fast this reaction is. Because I could think of two hypothetical reactions. I'll come up with a different reaction here. D plus 3E going to F. And maybe I'll say that in both cases, the rate of, so I'll call this reaction 1, and I'll call this reaction 2. Reaction rate 1, its rate law might be K times B squared. The rate of that second unrelated reaction might also go as the concentration of D squared. So I could think of two particular reactions. I can set them up just like I did today and give them, one might have a concentration of B, which is 0.1 molar, and one which has a concentration of D of 0.1 molar. So they have the same concentration, and their rate law tells me that the rate should depend the same way, but one of them might just naturally be a faster reaction because they're different reactions. They're unrelated to each other. What causes one reaction to be naturally faster or the other? That's encapsulated in the rate constant. So that's how it factors in here. Now, I didn't emphasize this, I think, enough in lecture, so I'll point this out right now. This 2, where did this 2 come from? There's no 2 in the balanced chemical equation. I'm hoping people might have been confused by that. And you should be. There is no way to predict what that exponent is just by looking at the balanced chemical equation. In general, your exponent in the rate law, what we call the order of the reaction, we'd say this reaction is second order with respect to B. The order of the reaction with respect to a particular reactant is completely unrelated to its molar coefficient. You can't predict it out of nowhere. So that's why you actually have to go, it's called a rate law, because it's observed experimentally. Scientific laws are scientific observations that are made over and over and over again. So you have to predict, you have to go into a lab and determine that. You can't look at a chemical equation and then predict the rate law. If you have a mechanism, you can do that, but not if you just have a chemical equation. So that's just one little side note, and we'll discuss that maybe a little bit more on Friday. How do you use and calculate the rate constant? Really pointed question. I didn't give you any guidance about how to do that today because that was not my learning objective for today. I just wanted people to be kind of aware that the rate of a reaction depends on concentration. There is an equation to describe that fundamental dependence, that there is a rate constant, and that the rate of that reaction can go as the first power, the second power, the 0th power even. That's all I really kind of wanted to get through, and how you could visualize that graphically. We're going to talk more about how you use rate constants and how you calculate them and how do you relate them to actual experimental data more on Friday. I have that's what we're going to do on Friday. I would have liked a few more examples to solidify concepts. I think examples are always good. I agree with that. If you as far as example conceptual questions are all tougher to come up with because they're all fairly not unique, but there's only a few key concepts, and you can mission match them a few ways, but it's harder to come up with those. Much easier to come up with sample example calculations, because frequently there's only a couple of ways we want to calculate things, and I can just switch out the numbers, switch out the equation or the reaction, and it's going to be the same basic calculation. So I will give people some practice with that. but we're going to do that on Friday. I think it would be helpful if we solve a few more problems in addition to all the conceptual methods of understanding. I agree, it's great for you guys to work through problems. Wholeheartedly, you'll get no argument from me that you guys should be doing problems. However, in my own perception of how class time goes, it is not as helpful. Again, this is my conception, so I could be wrong, but this is how I'm trying to, why I do what I do. I don't think it's as helpful for me to work through a problem, because frequently, especially in a lecture format, because when you're working through a problem, you really need to have like a back and forth. The real point of doing the problem isn't so you know how to solve the problem. The point of doing the problem is so that you can learn how to think critically and solve similar or alternate problems on your own. And the only way you can learn how to solve problems is to get practice solving problems. So me showing you how to solve the problem is not going to give you that type of experience. Let me give you an example. If you want to learn how to cook, you don't necessarily learn how to create recipes, how to cook from scratch, if all you do is follow recipes. So I'm guilty of that. I would say I don't know how to cook. I am really good at following a recipe. I've got a few skills I know how to apply, and if you give me a recipe, I can follow it to a T. But if you gave me a handful of ingredients and said, make a meal out of this, I wouldn't know what to do. And so that's kind of what I would like people to kind of get to, is getting experience. Here's a question, here's some data, try to solve the problem. And it's that act of solving it where I really want to get people to do. So me getting up and just essentially showing people how to solve the problem, that's really tough to do effectively in a lecture format. So I encourage people to come to office hours, come to my office, and I will help you work through problems. Absolutely. I love doing that. You can talk to other people in the class who come to work on numerical problems with me, and I am all for doing that. It just doesn't work as well in lecture, and I think that it doesn't help people as much. Lecture time is a better time for you to ask conceptual questions and for me to pose conceptual questions. Me doing a bunch of math on the board, people end up just trying to scramble and copy down the math and figure, I'll understand the math later. So I don't think it's the most effective way to do it. That being said, I will try to, on Friday, my plan is going to do something a little bit different. I'm tentatively planning to do a worksheet style exercise, a series of exercises in class on Friday, and that will give people some more experience doing these types of calculations. So I'll be moving around, I'll have people working on it, and that's what we'll be doing. So you will get some practice with it. Okay, last bit of feedback here. Sometimes points become scattered on the board while you're writing things on the board, and I lose track of things. Yeah, that's on me, and that's good. That's good critique. I need to work on my board management. So you know, I will try to working on that wholeheartedly. Okay, so that was all your feedback from today. If you have any further questions or concerns, please feel free to drop by my office or send me an email, and I will see everybody either tomorrow in lab or on Friday in lecture. Have a good day, everyone.